In a few minutes, we're going to show that the continuous image of a compact set is compact. And that may not make too much sense to you right now, but we'll explain what that means in a few minutes. But before we prove that's true, we need to prove this lemma first. The lemma says that if E is a compact set, and Xn is a sequence in E, then there exists an X naught in E, and a subsequence of this sequence Xn, here's the subsequence, X sub nk as k goes to infinity, that converges to that value X naught. So let's go ahead and prove it. It should only take about 4 or 5 sentences. Well, the first thing we want to observe is that since E is compact, it's also bounded, right? Remember from a little while ago, we defined for the real numbers in real analysis, a compact set just means it's closed and bounded. So, compact implies bounded. If you want to put a note in there that says compact implies bounded, that's just fine. I'll leave that out. Since E is bounded, so is the sequence Xn. Obviously, because these are just numbers taken from E. All right, so if we have a bounded sequence, do you remember the Bolzano-Weierstrass theorem? The way it's listed in the book is it says that every infinite bounded set has an accumulation point. But the Bolzano-Weierstrass theorem for sequences says this: by the Bolzano-Weierstrass, I'm just going to write BW, theorem for sequences, and we're talking about bounded sequences. That says that every bounded sequence has a convergent subsequence. X in K, K going from 1 to infinity. Let me see, by the Bolzano-Weierstrass theorem for sequences, I need to say there exists a convergent subsequence. X in K. All right, since we have a convergent subsequence, let's define what the limit of that sequence is. Let's say that we'll let X naught equal the limit as K goes to infinity of X sub nk. So this subsequence converges to X naught. Well, let's see. What are we trying to prove? I guess we're now trying to prove the only remaining thing is we have to show that X naught, the limit of this sequence, resides in the set E. So, observe that either X naught is in E, or X naught is an accumulation point of E. And I'll specify why we know that. It is by Theorem 1.17. But to finish this off, since E is closed, and if you want to justify that, you could put in parentheses or in a bracket, compact implies closed. Remember, we already used the fact that compact implies bounded. Compact means bounded and closed. Since it's closed, it contains all of its accumulation points. Therefore, E naught or X naught being an accumulation point, if it is an accumulation point, then it's contained in the set E. So we've covered all the bases. So let's see, but since E is closed, we see that X is an element of E. That's by the definition of a closed set. It contains its accumulation points. That's the end of the proof.